AP Calculus AB, Unit 10, Day 1. Sort of an introduction to what we're going to be covering in this unit. We're going to do a lot of area and volume, some new applications of the integrals. So just to kind of get you thinking of some of the different things we're going to talk about, we're not going to be doing, today's homework is more just practice of some of the same kind of stuff we were doing last unit. So that'll be good preparation for a retest on Unit 9. But I am going to start discussing some of these volume ideas. We do know some, geometric formulas for volume. We've even been using them this year. The volume of a cone is 1/3 pi r squared h, where you have a radius of the base and you have a height. So we can think Archimedes for that. That one's a little harder to memorize. I feel like cones and spheres. Cylinders, I feel like pretty easy to remember because I just think of cylinders as prisms. They're not technically prisms. Prisms have bases that are polygons, straight sides. Cylinder doesn't have straight sides, but it's the same idea that you multiply through by the area of the base of the shape times the height. And for a cylinder, the base is a circle, so it's pi r squared h. But you could kind of think of it also as like we could calculate the volume of a bunch of short cylinders, slices, and add them up, and that would give you the same result. Straighten the camera out a little bit, if it will. Okay. Now, this shape, three-dimensional shape, call these solids, kind of looks like a vase for flowers or something like that. How would you find that? Is there a formula for that? No, not a formula. And vases come in all kinds of different shapes. So even if we bother to come up with a formula, it'd probably not be very useful. So how do we find the volume of this shape? And the key is going to be slicing, which is an idea that we've been using all year. We're going to slice it into thin, flat slices. In fact, we might use kind of like cylinders. We'll assume that the edge of the thin slice is straight up and down, even though it's technically curved. And then we could add up all these short little cylinders as an approximation. Now, if we did more slices and made them thinner and thinner and thinner, it would get closer to the actual value. So here's another sort of application of the slicing idea. Think of like a loaf of bread or cheese or a stack of paper has, you could think of it, things that are actually naturally or already sliced. And then we could just add up each slice. So one type of problem that we're going to be looking at, I think starting tomorrow, is volume by cross-section. They call it volume by cross-section because the cross-sections are going to be prescribed what kind of shape they are. And it's kind of like we're building the volume of this one off with this assumption that every cross-section has the same shape. So there's going to be some base region created by some curves or boundaries. And so this is our base region, and we're going to build up from the bottom here. And the shape of this is going to impact the volume. So we're going to make the slices half of a circle. And so I think it's often good to at least draw one of them. Today we'll draw some more just to kind of see what the idea is. And so we have this, and I'm trying to give it some dimension, but it has a thickness to it. But there's a bunch of slices. There's one here. In fact, we could say there's infinite slices. And when you start to connect them, you start to see sort of the shape, right? This actually almost looks like half of the vase that we were just looking at, kind of like half of the vase on the side. So the thickness, and it depends, if we slice it vertically, the thickness is going to be dx, right? But we could slice it horizontally. It would actually give you a different shape. So it's not really a option. It's going to be, you're going to be told, okay? And so, yes, the area and the volume of each of these slices changes. It's getting smaller. It depends on the distance between those. So the volume would be some cross-section area that I might generically just call A as a function of x. As you go along x, it changes the area times, so it's the area of this times the thickness gives you the volume, right? And we would go from 0 to b in this problem. Now, this is something I like to do. I would say, okay, I'm going to actually just draw a simple picture of the thing we're trying to find the area. If it's half a circle, then I might go ahead and say, okay, well, half a circle would be 1/2 pi r squared dx, right? But then to actually integrate this, I can't integrate something with r's with respect to x. We need x's here, right? So actually the radius, by the way, of these slices is the y value divided by 2. So that actually might be the next thing we could write in there. Now, we could, the pi and the 2 and stuff, we can move those out in front. The radius is the y divided by 2. And the divided by 2 has to get squared. And then we could, because this whole diameter here, by the way, the diameter equals y. Whatever the height of this curve is gives you the diameter, right? So, and then, inevitably, we will have a function for y in terms of x that we could plug in there. So that would be sort of our last step to being ready to go. We could say, oh, let's put the function in there. Now, usually you would actually have an expression with x's in it. So that's going to be one of the kinds of problems. So, we needed the radius in terms of x. We know that the diameter equals y, and therefore the radius equals y over 2. So we're going to do some of those in the coming days, not on today's homework. And then another type of problem where this volume is generated by these slices coming off the base. This volume is going to be generated by spinning a two-dimensional region around some axes. And it might be the x or y axes, or it might be some other vertical or horizontal line. We'll stick with vertical and horizontal lines, but it's going to be spun around this. So some region determined by some different curves is going to be spun around it. And you're going to get a volume. Now, just to kind of give you an idea, we don't really need to draw these all slanted like that. I might do it on some of the notes and stuff, but you can probably just draw it straight on. And then it's good to indicate where you're going to spin it around. And the trick, because this is going to help you set the problems up correctly, because these aren't super easy. The trick is I usually redraw the region on the other side of on the opposite side of the axis of rotation. Just try and draw a mirror image of it. But then that kind of helps me start to sketch it out. Now, the cross sections of these are always going to be circular, because it's made by spinning it. And you could start to get a really good idea of what's going on here. Now, on the homework, I'm usually just going to draw one cross section, just a single one in the middle usually. I don't need a beautiful picture. I'm going to draw kind of a cool one right now just so you can kind of envision it, which is, it's probably its best purpose. But for setting the problem up, it's going to be too busy. But, you could even add some more lines here, kind of see the outside of it. So it has this hole that goes through it. And I guess this is kind of, so this is like, and I'm going to just add some more texture kind of to it to kind of emphasize the different surfaces, right? You can see you could put like something through this hole, right? So we're going to be finding these volumes, and a lot of shapes are created sort of by revolving something around. Now, tonight's homework, though, we're going to be focusing on just area, which we were talking about before. And but I'm going to give you maybe kind of some new variations of the problems. But let's do a couple examples. Find K such that the vertical line x equals K splits the enclosed area between y equals x squared and the x-axis, and for 0 to 6 into 2 equal pieces. So you got to see, well, the enclosed area between y equals x squared, the x-axis, and 0 to 6 is this area right here, right? So that's the area we're talking about. And we want a vertical line that cuts it in half, two equal pieces. So some vertical line has got to cut it into 2 equal pieces. And they say x equals k. So we could draw that right here, x equals k. So we're trying to figure out, well, what is that line that will cut this perfectly in half? Do you think it's going to be at 3? Probably not. Is it going to be right in the middle at x equals 3? Probably not, because I feel like we have a lot more area on the right of that. So I think it's got to be closer to 6, right? It's not going to be close to 0. I mean, you can just look at this picture, and where would you have equal amounts of area on both sides? Well, it's got to be a little more to the right, because there's just a lot less area on the left, right? So probably not that. Is it the same location as like F average, which is something we were calculating in the last unit, mean value theorem for Y? I don't know. We could check it out we could confirm it. But let's, how are we going to do this? I think we probably need the area that we're supposed to cut in half, right? So we probably should find the area first so that you can figure out what half the area is. So we're going to find the area, and this is a pretty common exercise for us. I'm going to go 0 to 6 of x squared dx. The antiderivative is x cubed over 3. 0 to 6. We're going to plug 6 in. It's going to be 6 times 6 times 6. So 1 and 6s and 3s will reduce to a 2 times 36 is 72. We plug 0 and we get 0. So it's going to be 72. That's the entire area, right? Then we should probably find half of the area. And we're usually not going to write all these steps out, but probably going to find half the area, which would be 36 in this case. Now, here's the tricky thing. What we're going to do is we're going to take half the area and set it equal to the integral of the function. And I guess I could write this more as as a strategy. We're going to say half the area equals the integral of the function from, say, 0 to k. So we can actually put variables that we're trying to find in the limits. So in this case here, we'll say, okay, well, we're going to integrate x squared dx from 0 to k, and it should give us 36. So we're trying to figure out, well, how far do we integrate? We're going to integrate until we get to a value that gives us 36. Now, alternatively, you could do k to 6 instead, and that should give you the same answer. I think I like working with 0 better than 6. Like 0 is usually going to make the calculations a lot cleaner. So you could do either one, but I would lean towards using 0. I think it's going to make the work easier. So now we actually, even though we already integrated it, we have to integrate this. We've got to find the antiderivative, x cubed over 3, power rule. Bump it up 1, divide by the new exponent. Still have 36. we're going to plug the limits in like we usually do, but now we're plugging a k into one of the spots. But now we have a polynomial that we can solve for k. So, we can multiply both sides by 3, and we're going to get, 108. Then we could take the cube root of both sides, no plus or minus. It's an odd root. And, so we could write the answer as cube root of 108. We could, I don't know if we could actually take any perfect cubes out. I think so, actually. We could say this is 3 cube root 4. On a calculator, it's going to give you 4.762. So this is the k value. This is how we do it. So this is a new kind of problem. You're going to have some on today's assignment. They will be on your next test, okay? And now, here's the question. Does this happen at the same place that f average happens? I don't know. This might be interesting to check it out. So I'm going to just calculate. This is just good practice anyways from your last test or your retest. So the formula for f average. Now, I don't memorize this formula. As the idea, I say, okay, well, let's take the area under the curve from 0 to 6, right? And then divide it by the base of the rectangle. It's like we level it out. Remember that? We level the area out. And the base of the rectangle is the distance between the limits. So for us, that's going to be 1 over 6 minus 0, 0 to 6 of x squared dx. This is some of the same work we already did. So, this is the area that we found. This should be 72, but we could do the work again if you want. So we are going to get 72. And then we're going to get 12. Now that's f average. That's the y value, the average y value. So then to find the location of it, the c value or whatever, we would set it equal to the actual function. Say, okay, well, f average equals 12. So let's take the actual function, y equals x squared, set it equal to 12, and solve. You take the square root of both sides, plus or minus this time. We get plus or minus 2 root 3, which on a calculator is 3.464. The positive one is the one we would want for our c value, or x star, or whatever. But it is not the same place. So I don't know. It was an interesting question, but it isn't the same. They really have nothing to do with each other. So, all right, now let's take it one more step. Let's do it as a horizontal line that cuts the area in half. Okay, so it's the same area, right? So you would still, I'm going to skip those first steps, and we know that half the area equals 36. Okay, and that part you could still integrate it vertically, but now we're trying to find a line y equals k that cuts the area in half. So to find this value, we have to integrate it with horizontal slices. Okay, so we still have to do it with horizontal slices. So, but same idea. We're going to integrate it, but now we have to. These are our slices right here. So it's going to be x right minus x left. Right, x right minus x left. Slices have a thickness of dy. We're going to go 0 to y value 0 to this is 36. So the limit's going to be 0 to 36. It's the y direction. So x right is always 6. X left, we got to figure that out. We're going to take square root of both sides, plus or minus. So x equals plus or minus the square root of y. It's the positive one because we're on the right half of that parabola. If we were over here, we'd use the negative square root of y. So it's square root of y dy. And we're going to set it equal to 36. So same idea, but now we're dealing with horizontal slices and everything's y. So we're going to try and find the value of it should be, actually, it should be 0 to k still. You could do 0 to k or k to 36. We're going to go 0 to k or k to 36. I think the 0 is easier. We got to find the antiderivative. This is the same thing as a 1/2 power, right? So the antiderivative is going to be 6y minus y to the 3/2 divided by the new exponent, multiplied by the reciprocal. Then we're going to plug k in. We're going to have 6k minus 2/3 k to the 3/2. You plug zeros in, you get zeros, equals 36. And I don't think we're going to be able to solve this by hand. I don't think we're going to pull this off. So we're going to go ahead and use our calculators. So I'm going to solve with my calculator. Now, this is just a good skill for solving algebra equations with your calculator. The way I would do it is I'd move everything to one side, like I would if I were to do it by hand. Move everything one side, equals 0. You don't have to, but it's going to make it easier. Everything on one side equals 0. And I'm going to put it into the Y menu. Now, these are K's, but we're just going to put X's. Okay. You know, we're just going to use X's because that's the only thing that you can type in your calculator as a variable right here, right? X. Like we can't put K's in. If you put these K's down here, these are just memory locations. It's not going to work. It's just for storing some value in the memory. It's not the same thing. So we got to put X's. 6x minus 2/3 x to the. Now, if you do 3/2, you got to put parentheses around it. Otherwise, it's going to do it to the third and then divide your answer by 2. You could do it without parentheses if you just type in 1.5, right? Minus 36. So I put it in there. And then I'm going to graph it. I'm going to go to the window, though, because I know the answer should be between 0 and 36, not 0 and 6, because remember, these k's are like our y values, right? It's somewhere between 0 and 36. 0 and 36. I really just care about seeing the x-axis because I just want to see what we're trying to do is find the x-intercept of this graph, right? That's the beauty of moving everything one side equals 0 is just look for the x-intercept. So since I'm just looking for the x-intercept, even though I know these are y's, I'll treat them like x's. I'm going to just go -1 to 1. Okay, so then I'm graph it, and I only expect to get one answer. So if you get more than one answer, that'd be weird. And then I calculate that 0. I want to find that x-intercept. So this is 0 to 36. So this is 0 to 18. I mean, it looks like it's around 8. So you could say like 5 to 15 or something. Guess 8. That just makes it a little quicker. It's actually 9. Okay. So k equals 9. Now, there is another way to try and solve equations on your calculator, like kind of a more official like program. I don't think it's good though. So it's under the math menu, and it's down here at the bottom, 0 solver, and it's meant to solve equations. But you have to have the equation in your Y menu, and then this tells you where you're looking for the solution, which is essentially the smallest number to the biggest number allowed in this calculator. And so then you hit enter, or I don't even know. I might have messed this up. Anyways, I would tell you not to use it anyways. So just use the graphing technique. So the strategy for solving this on the calculator is to graph this equation, set the window for the x's, which are our k values, our y values, between 0 to 36. So just restrict it to where you know the answer should be. If you don't, you might get other answers that aren't even supposed to be considered, right? And then the y values, I would just do -1 to 1. And then you would find the 0, the x-intercept, the 0, by doing a second trace calc. And then pick 0, which was option number 2. And then you tell where to look for it. And the closer you tell where to look for it without spending too much time, the quicker you get your answer. Okay, so if you have a horizontal line, you have to do horizontal slices. The original area, you could do vertical slices still, if you want. I mean, we'd already done it. That area is not going to change. So that's it. Today's assignment is on the bottom, and it will have a couple problems like this on it, but it'll mostly be a bunch of extra practice of stuff that we were doing last unit and that you were tested on. So go ahead, get some practice.